Yeah, so mm, we'll wait maybe 2 more minutes so that if others want to join, they can join, and then we'll start. Thank you. Uh, Meanwhile, if you have any doubts, feel free to ask. Okay. Okay, so I guess we can start, and if others want to join, they can join later. So since you don't have any doubts, let's start with some basic problems. So today we'll be solving problems based on week 5, and so week 5 is mostly simple harmonic oscillations. Okay, so today we'll be doing some simple harmonic oscillation problems, both undamped, damped, and then also some problems for the forced harmonic oscillator. So let us begin with the first problem. And this is a very straightforward problem. So let's have a look at it. A one-dimensional simple harmonic oscillator of mass 50 gram is attached to a spring of stiffness 809 per centimeter. Find the time period of the oscillator. Okay. So yeah, so we have a 1D oscillator, and the time period is simply 2 pi over omega, where omega is given by under root k over n. Okay, so this is the formula. We can also, if we don't remember how this formula is achieved, we can even do a quick derivation of this formula. So we know that for a simple harmonic oscillator, this is our equation of motion. So our force, so our force is directly proportional to minus k of x, and this k is nothing but the spring constant. And we can write it as this thing, and then we can define omega to be under root k over m, such that this equation becomes something like this. Okay, now this is a uh, defining equation of simple harmonic motion, and we know that the general solution of this equation, so the general solution of this equation is given by, so x of t is nothing but a cos omega t minus phi, where a and phi are the two constants that we get from integrating this equation. Okay, now this a is nothing but the amplitude, and this phi is nothing but the phase. Okay, so this is it. Now here we have this omega, right? This is under root k over m, and we know that this time period t is 2 pi over omega. So our t becomes 2 pi under root m over k. Okay, so now it is given that mass is 50 grams and the value of k is 800 dyne per centimeter. So mass is given to us to be 50 grams and the value of k is given as 800 dyne per centimeter. Okay. Now both of these values are in CGS units, so we can of course work in CGS units. And substituting these values, we get t as 2 pi under root 50 over 800. So this cancels out and this gives us 16. Okay, so this becomes 2 pi under root 1 over 16. And this becomes 2 pi over 4, which becomes pi by 2. Okay, so the time period of this simple harmonic oscillator is nothing but pi over 2 seconds, which is roughly around 1.57 seconds. Let's check the options. It matches with option B. So that is our answer. Okay, so this was a very simple problem. We know that omega is given by under root k over m, and then the values of k and m are given to us. So we find omega and then we find the time period. Okay. So let's move on to the next problem. The next problem is the displacement of the same oscillator. Okay, the displacement of the same oscillator can be expressed as this thing. This we have already derived. So they are calling the amplitude as C instead of A. So we can write our equation in terms of C, where C is the amplitude. So C cos omega t minus phi. And the initial displacement x naught. So x naught is the value of x at t is equals to 0. That is given to be 3 centimeters. And the velocity v naught is given to be 8 centimeters per second. So we have to find the amplitude c and initial phase phi. Okay, so clearly we can start with this equation that is given to us. Okay, and if we differentiate it, so let's differentiate with respect to time. So what we'll get? We'll get dx over dt, which is nothing but our velocity. So c is a constant, right? So c stays as it is, and differentiation of cos will give us a minus sine uh, omega t, and we will also have an additional omega. So our v of t we can write as minus c omega sine of omega t minus phi. Okay. Hmm. So now we have two equations, right? At t is equals to 0, we have two equations. So at t is equals to 0, we can write our x as x t is equals to 0, and this is nothing but x naught. So this becomes c cos of minus phi, which is nothing but c cos phi. Okay, and our velocity at t is equals to 0, which is nothing but v naught. This becomes minus c omega minus phi, sorry, sine of minus phi, which becomes c omega sine phi. Okay, so we have now two equations, that x naught is c cos phi and v naught is c omega sine phi. Now we have two equations and two variables c and phi. So we can solve both of these equations to find out the value of c and phi. So first of all, we can see, like, if we divide both these equations, so what we'll get, let's say this is equation 1, this is equation 2. So if we do 2 over 1, that gives us v naught over x naught, and that is equals to omega tan phi. Okay, and this implies tan phi is nothing but v naught over omega x naught. So this is the equation of phi, and to find out the equation of c, what we can do, we can divide equation 2, by omega. Okay, we can divide equation 2 by omega, and then square that equation, and then add that to the square of equation 1. So what that will give us is v naught over omega squared plus x naught squared is equals to c squared cos squared phi plus c squared sine squared phi. Now if we take c squared as a common factor, so this becomes cos squared phi plus sine squared phi, and using the trigonometry identity, we know that this term is simply 1. So therefore what we get is c is nothing but under root x naught squared plus v naught by omega squared. And I'm only writing the plus value because it is the amplitude, and we only care about the magnitude and not the direction. Okay, so we have derived both the results for the value of phi as well as the value of c. Only thing that remains now is substituting the values of V naught, omega, and X naught. Okay. So yeah, so this was our omega. So 2 pi by omega. So T was 2 pi by 4, and this was equals to 2 pi by omega. So this implies omega is nothing but 4. Okay. So let's write here that omega is 4 and x naught is 3 and v naught is 8. So if we substitute all these values here, we get tan phi is equals to 8 over 3 into 4. Okay. So this becomes 2 over 3. So phi is tan inverse 2 over 3, which comes out to be roughly 0.58 radians. And for the value of C, we get under root. Okay, now so this is 3 squared plus 8 over 4 squared. So this is under root 9 plus this is 2 squared is 4. So this is under root 13, and which comes out to be roughly 3.6 centimeters. 3.6. Okay, so this is our phi and this is our C, which matches with option A. Hmm. Right. Okay. So we have now found out our amplitude. We have found out our phi. We know omega. So basically we know everything that is needed to solve this problem. And now based on this problem, like question 1 to 2, we are asked to find the total mechanical energy of the oscillator described in questions 1 and 2. Okay. So we know that the energy of simple harmonic oscillator is this thing, which is the kinetic energy plus the potential energy, right? And we know that this entire thing is a constant. Okay, this is a constant, and because this is a constant, we may evaluate the value of E according to our convenience. So let us consider the instance of maximum displacement. So at maximum displacement, what will happen? Our x will be C, right? So it has reached the amplitude. And this, because this is a turning point, so our velocity, instantaneous velocity at that point is 0. Okay. So if we substitute these two values in the equation above, our energy equation reads as, so the first term just goes to 0 and our energy equation just reads as half k c squared. Okay. Okay, and so now we just computed that C is under root 13. So this implies C squared is 13. And also K was given to us as 800 dyne per centimeter. Okay. And this is also centimeter. Right. So let's just plug in these values. What do we get? We get E as half into 800 into 30, which is nothing but this cancels out. This becomes 400. This becomes 5200 ERG. So this is what we get as our answer, which is option D. Now we can, what we could have also done, instead of taking this maximum displacement point, we could have taken the zero displacement. So we could have also done at, sorry, at x is equals to 0, right? At x equals to 0, or like x naught, which is our initial conditions. At x is equals to x naught, so our energy E, we can write half m v naught squared plus half k x naught squared, right? So the mass was given to us as 50 grams. So this is 50, and v naught was given to us as 8 centimeters per second. So this becomes 64. And then we can add this k as 800, and x naught was given to us as 3. So this becomes 9. Okay. So this first term, so this, let's cancel this out. This becomes 32, 16. So this is 1600. Okay. And the second terms will give you 4. So 36. So this gives you 3600. So adding both these two will again give us 5200 ERG. So both of them are exactly the same, which again goes to show us that the energy is conserved, and we could choose any point as per our convenience. Okay, so this was all about simple harmonic oscillators. Now let's consider like small oscillation kind of problems. So here it is given to us in the next problem that we have a particle of mass m that moves in one dimension under the potential v of x is this thing. Okay, so this is not a simple harmonic oscillator but some other potential, and we have to find the angular frequency of small oscillations about a stable equilibrium point. Okay, so right now, for any potential v of x, for any, I should write smooth potential because we want to differentiate it. For any smooth potential v of x, and let's say it has an equilibrium point at x is equals to some x naught. This is the equilibrium point. Okay, we can Taylor expand the potential, and that gives us something like this. So the first term is v at x naught, then we get the derivative at x naught and minus this x minus x naught. Then we get the second derivative at x naught and x minus x naught whole squared, and so on. So this is just a constant, and we can set our reference of the potential energy anywhere. So we can set our potential, we can set our reference of potential energy such that set reference such that V x naught is equals to 0. Okay, so we can do that. And then because x naught is equilibrium point, because x naught is equilibrium point, so the potential must have a minima there. Therefore, V prime at x naught must be 0. Okay, so the first term is 0 and the second term is 0. What this allows us is to write V of x to be almost equals to half of V double prime x naught, which is the second differential, times x minus x naught whole squared. Okay, and we can neglect the higher order terms because we are just considering small oscillations, right? Near equilibrium point at x equals to x naught, right? Okay, and in the question also, they are just talking about small oscillation. So this is the general equation. Okay, and clearly you can see that if we have a simple harmonic oscillator where our v of x is nothing but half kx squared, if you differentiate it once, it gives you v prime x is equals to k of x, and because this has to be 0, this implies x is equals to 0 is the equilibrium point. And then if you differentiate it again, we get just k. So if we put these two, that the double differential is k and x naught is equals to 0, right? X naught is equals to 0 in this equation. So you can see we recover back our simple harmonic oscillator, right? Okay. But the potential that is given to us in the problem looks a little different, and we have to find out k. Okay. So yeah, so what this k is, so this, yeah, so if we compare this with our simple harmonic oscillator, which is v of x is half k x minus x naught squared. This is the simple harmonic oscillator problem. So upon comparing, you can see that k is nothing but this differential, right? So the effective spring constant let's call it k effective, that is nothing but v double prime x naught. Okay. Okay. And therefore omega, what do we need to find? We need to find angular frequency. Therefore, near stable equilibrium, omega can be found out simply as v double prime x naught over m. Okay, so that's it. And now we can just plug in the values for this given potential. V of x is ax4 minus bx2. So the potential that is given to us is v of x is ax to the power 4 plus, sorry, minus bx squared So if we differentiate it, what do we get? We get v prime of x as 4a x cubed minus 2bx. We can take x outside, so this becomes, let's take 2x as common. So this becomes 2a x squared minus b. Okay. To find out the equilibrium points, we set v prime x as 0, v prime x naught as 0, and this implies x naught is either 0 or x naught uh, or x naught squared is equals to b over 2a, right? So we get these three uh, equilibrium points. Now let us find out what is our v double prime. So v double prime of x then becomes 12a x squared minus 2b. Okay, also let's find out. Okay, it is given that both a and b are greater than 0. Okay, so both are positive. So yeah, so if we put x is equals to 0 here, if we put x is equals to 0 in this equation, so we get minus 2b. Okay, so at x is equals to 0, v double prime of x is less than 0, which is minus 2b. So this is unstable, right? Because we have a maxima here. Rather, if we put this condition that x squared is b over 2a, so if you substitute b over 2a here, a and a will cancel. So this becomes 6a minus 2b. Sorry, 6b minus 2b. This becomes 4b. So v double prime of x is 4b, which is greater than 0. So this is stable. Okay. So this is the value of x naught, right? So this is the x naught we are concerned about. We want to find out the frequency of oscillation about this x naught. Okay. Right. So that we have already done. So let's just plug in this value of v double prime x in this equation of omega. What then our omega becomes simply under root, and then this is 4b over m. We can take 2 outside, and then this omega becomes 2 under root b over n. So this is 2 under root b over n. This is our omega, which is option C. Okay, so this method that we discussed is a general method, right? Irrespective of the potential that is given to us, what we need to do is we need to first find out the first derivative, like here. So find out the first derivative, set the first derivative to be equal to 0, and that will give us some equilibrium points. Okay, then we find out the second derivative. This is the second derivative, and at those equilibrium points we check whether those points are a stable equilibrium or unstable equilibrium. So we check that and we get stable or unstable equilibrium. And because we want the particle to oscillate about a stable equilibrium, so we use the value for v double prime of x obtained at the stable equilibrium. And that value is nothing but our k effective, right? As we discussed, the second derivative that second derivative just gives you this effective spring constant. And from that, you can easily find out the value of omega. Yes. So yeah, so this is a very general method, and if you have any potential, then you can use this method to solve the problem. Okay, so let's look at the next problem. The next problem has a simple pendulum of length this much, and it undergoes small oscillations, and we have to find the time period. Okay, so for a simple pendulum, the restoring, yeah, so for a simple pendulum, we know that the restoring torque about the pivot theta is given by minus mgl sine theta with so the torque, if I write torque for a simple pendulum, that is nothing but m minus mgl sine theta, and the moment of inertia I is nothing but ml squared. Okay, so if I do the second law, I theta dot is equals to tau, this gives me theta double dot is equals to minus, okay, maybe I should write this as ml squared theta double dot is equals to minus mg l sine theta. So my m's will cancel out, this square cancel out this l. So theta dot plus g over l sine theta is equals to 0. This is the equation of motion for a simple pendulum. Okay. Now, because we are asked only about small oscillations, okay, we are concerned only about small oscillations. What we can do, we can make the approximation sine theta as theta. Okay, so we can make this approximation, and this then implies that our theta dot plus g over l theta is equals to 0. Okay, and this is exactly the simple harmonic oscillating equation, right? This is the simple harmonic oscillator, and we know that this middle term, sorry, this coefficient of theta is nothing but omega squared, right? If we compare with the standard simple harmonic oscillation equation, which is theta dot plus omega squared theta is equals to 0, on comparing these two, we get that our omega squared is nothing but g over l. Okay, this is our omega squared. So time period t is nothing but 2 pi over omega, and this becomes 2 pi under root l over g. Okay, so this is the equation. Okay, and now length is given to be 2.45 meters and g is 9.8. So if we substitute here 2.45 and this is 9.8, and we take the square root of this thing. So this is just 1 over 4. Okay, and so the time period t is nothing but 2 pi over 2, which is nothing but pi. Okay, so our t comes out to be 3.14 seconds roughly. Okay, 3.14 seconds. Okay, which matches with option A. Yeah. So this is the formula that the time period of a pendulum is given by 2 pi under root L over G. And as you can see, it depends only on the length of the pendulum, nothing else. It does not depend upon its mass. Okay, it only depends on its length. Okay. So this was it. Okay, let's look at the next problem. So we have two masses, okay, m1 and m2, and they are connected by a spring of stiffness k is equals to 40. Okay, so we have uh, two masses m1 and m2, and they are connected by spring. Okay, so let's say here I have my m1. Okay, maybe I should draw better. Let's say this is m1, and let's say here I have my m2, and they are connected by a spring, and the spring constant k, and the spring constant is k. Okay, and they are kept on a frictionless surface, so that there is no friction, and we have to find the angular frequency, of oscillation of their relative separation. Okay, so let's say uh, let's say this is our origin O, and this is our x-axis. So this distance is x1, right? This distance is x1. This distance is x2. So the separation between them, both of them, is x1 minus x2, right? This distance is x1 minus x2. And let us consider that the natural length of the spring, let's consider that this is the natural length of the spring, L naught. Okay, so such that there is no tension in the spring, but we have extended it, we have stretched our m1 little outside by some displacement s. Okay, so L naught is the natural length of the spring, and we have pulled our m1 out by some distance s. Okay, so then what we can do is we can write, okay, so this, you can see this distance is, so s plus L naught, which is the separation between two blocks. This s plus L naught is nothing but x1 minus x2. Okay, and this separation, oh sorry, this stretching s, we can then write as x1 minus x2 minus L naught. Hmm. Okay, so yeah, this is the equation that we have. So now for these individual blocks, we can write the Newton's second law. Okay, for these individual blocks, we can write this Newton's second law. So the force m1 x dot will be minus k of s, and the force m2 x double dot will be plus k of s, right? So one will be pulled in one direction, so that the other is pulled in the other direction. Okay, so like subtracting these equations and then dividing, also from this equation s, we, if we differentiate this differentiate this. Okay, let's call this equation 1. So we differentiate 1 with respect to time twice. So that just gives us s double dot is equals to x1 double dot. Okay, so sorry, this will be x1, this will be x2 minus x2 double dot. And because L naught is a constant, so if we differentiate it, we just get 0. So this is what we get. Now we can divide this equation by m1, so we get this thing, and this equation by m2, so we can get this thing. Okay, and then if this is equation 2, so we can substitute equation 2 here. So substituting equation 2, we get s double dot is nothing but minus k over m1 s plus k over m2 s. Now if we take minus ks as common, so we get s double dot as minus ks 1 over m1 plus 1 over m2. Okay, now we are going to define a new quantity 1 over mu. We define this as this quantity in the bracket 1 over m1 plus m1 over m2. We define it so that we can write the above equation in a familiar form minus k over mu s. Okay, and this mu is known as the effective mass. Okay, so it also has a name for it. Now this, oh sorry, not this is not the effective mass. This is called reduced mass. Okay. So this relative coordinate s, okay, the relative coordinate s, now this obeys simple harmonic motion with reduced mass, okay, in place of n. So the omega for this reduced mass will be simply k over mu. Okay, so for a two block system, what we have done essentially is found out the reduced mass of the two masses, and then instead of using their actual masses, we just have to use their reduced mass to find out the frequency of oscillation. Okay, so for the masses given to us m1, m2, this is 2 kg and 8 kg. So our 1 over mu will be 1 over 2 plus 1 over 8, right? So this becomes 4 over 8. So this becomes 5 over 8. So our 1 over mu becomes 5 over 8. This implies omega is nothing but, and k is given to us as 40. So 40 into 5 over 8, and this gives us 5. So omega is simply 5 radians per second. This is the value of omega that we are getting. Okay, which is option B. Okay, so in practice, what we have done is we had in the beginning we had two masses m1 and m2, and then by doing some math we find out that the behavior of two masses is such that is as if like it is behaving like a single mass but with a reduced mass. Okay, so it is behaving like a single mass which has this reduced mass given by this equation, and then everything else remains same. So for omega we put out this value of mu which has this contribution from both m1 and m2, and this dictates the oscillation. Okay, that's it. Okay, so yeah, so let's take a small break before we solve the next problem. I'll be back in a minute. Okay, so yeah, let's try to solve the next problem. We are given an oscillator of mass 0.5 kg and it has natural angular frequency omega naught, and it is driven without damping by the periodic force this much, and we have to find out the amplitude of the steady state, which is the particular solution. Okay, we have to find out its steady state solution. Okay. So for a forced oscillator, okay, for a forced oscillator, the equation of motion mx double dot plus kx, instead of being equals to 0, this is now equals to f naught cos omega t, because this is the external force. Okay, so we can rewrite this equation as x double dot plus omega naught squared of x. This omega naught is the natural angular frequency, and f naught over m cos omega t. And this omega is the frequency with which the oscillator, sorry, this periodic force is acting upon our oscillator. Okay, so omega naught and omega are different. Okay, omega naught is the natural frequency, which is given simply by under root k over m, and omega is the driving frequency. Okay, so for steady state, right, we have to find out the steady state. For steady state, we can try, let's try that xp is some c cos omega t. Let's try this as the solution in the equation of motion. Okay, so if we try this thing, so taking its double derivative, this will just give us an omega squared factor outside. So we'll have minus omega squared c cos omega t. This is the first term. And then we have omega naught squared c cos omega t. And this is nothing but f naught by m cos omega t. So we can cancel out all cos omega t's here, and then we can write we can take c as common, and this becomes omega naught squared minus omega squared is equals to f naught over m, and this implies c as f naught over m omega naught squared minus omega squared. Okay, so this is the equation that we get. uh, so this is our steady state solution, and this is the amplitude of the steady state solution. Okay, and this is exactly what we needed to find. So we need to find the amplitude of the steady state solution. And now we have calculated the value of c, which is the amplitude, in terms of f naught, m, omega naught, and omega. Now this f naught is given to us as 2. So let's write it down. So this is 2. The mass is given to us as 0.5 kg. So this is 0.5. And omega naught is 10, whereas this omega is 6. Right? So this becomes 10 squared minus 6 squared. Okay. So our C is then 2 over 0.5 into, this is 100 minus 36. This is 64. And 0.5 of 64 is 32. So this becomes 2 over 32. And we can write it as 1 over 16. Okay. And we know that 1 over 16 can be written as 0.0625 meters. Okay, if I write it in centimeters, or C is 6.25 centimeters. Okay, so option D. Okay. Okay. So this was a problem based on forced oscillator. Now we have another problem based on undamped force oscillator. Okay. So the question is, for an undamped forced harmonic oscillator, how does the phase of the steady state response relative to the driving force change as the driving frequency omega is increased through the natural frequency omega naught? Okay, so we just found out that the amplitude C, we can write it as f naught over m omega naught squared minus omega squared. We can write this as. And now we want to look at the sign of C. Okay, if this C is greater than 0 or less than 0. Okay, if omega is less than omega naught, so this quantity, the denominator is then positive. So this implies C is greater than 0. Okay. So this implies that our equation of x, which was C cos omega t, and this C is positive. So it has the same sign as the driving force, which is F naught cos omega t, right? Our driving force F is F naught cos omega t. So now this xp has the same sign as F, same as F. So we call this as in phase, right? Both of them are in phase. However, if omega is greater than omega naught, then you can see this term is negative. Sorry. So this implies C is less than 0. And then our xp, we can write it as minus mod C cos omega t. Now this is opposite to F, opposite to F. So this is out of phase. Okay. And as if both of them are equal, if omega is equals to omega naught, then our C diverges and goes to infinity, and this is known as the undamped response. Okay. So this is the undamped response. Now what the question says is, how does the phase of the steady state response relative to the driving force change as the driving frequency omega is increased? So you can see we are increasing omega, we are increasing omega. If I make a plot, okay, let's say this is omega, this is omega, and this is the, sorry, this is omega, and let's say this axis, this is our phase phi, and this phase is between C and F, right? So phase between C and F, which is the amplitude and the external force. Right. So when omega is 0, when omega is 0, you can see that C is positive. And let's say this is some particular omega naught. So when omega is less than omega naught, this phase is, so they are in phase. So there is no phase between them. So clearly a 0 phase up to this point. And then there is a divergence up to infinity at this point. And after this xp, when omega is greater than omega naught, we get a minus sign, which is out of phase. So we get a phase difference of 180 degrees, right? Or pi by 2. So after this, we get a phase difference of pi by 2. Okay. So this is how this thing looks. Okay. So here you go. And now let us look at the options. Okay, sorry, this will not be pi by 2, but because this is 180, so this will be pi. Right. So if we look at option A, it shifts abruptly by pi radians as omega crosses omega naught. Yeah, so this is exactly what we see. It shifts gradually and continuously from 0 to pi. So this is wrong. It remains exactly in phase. This is also wrong. And it shifts exactly pi by 2 precisely at omega equals to omega naught. This is also wrong. So the correct option is option A. Okay. That is the correct option. Now at exact resonance, the undamped oscillator equation has a particular solution of which form? So we just now saw that at omega is equals to omega naught, our C was diverging, right? Our C was diverging. So that solution, uh, the solution that assumed, we assumed this solution, right? C cos omega t. So for omega is equals to omega naught, we cannot assume this solution because at omega is equals to omega naught, our C is diverging. Okay. Okay. So instead, we can, what we can do is we can try this solution where we multiply a constant t. Okay. So now, if we differentiate, okay, now this is the equation. Let us also write the equation. X double dot plus omega naught squared x is equals to f naught by m cos omega naught t. So first thing we need to do is we need to do the double differentiation, and upon differentiating twice, so let's differentiate this equation. So xp dot just gives you a cos omega naught t plus b sine omega naught t, this thing, plus t minus omega naught a sine omega naught t plus omega naught b cos omega naught t. Okay. And if we do the second derivative, so we get a minus omega naught a sine omega naught t plus omega naught b cos omega naught t plus t, and this same equation, which is minus omega naught a sine omega naught t plus omega naught b cos omega naught t, and we'll get one more equation which will be plus minus omega naught squared a cos omega naught t minus omega naught squared b sine omega naught t. Okay, so we get this equation. Now these two terms are exactly the same. So what we can do is we can write x double dot of p, we can write it as 1 plus t, and let's take out omega naught outside, and so this, okay, maybe we can also take a minus sign outside, so this is a sine omega naught t plus b cos, sorry, minus b cos omega naught t, and then we also have minus omega naught squared, right? We have this thing which is minus omega naught squared, and this is simply a cos omega naught t plus b sine omega naught t, right? So this is just xp over t. That's it. There is nothing but xp over t. Okay. And if you see this second, so this exactly matches with the second term, which is if we put x as xp here, this matches with the second term. So basically, then what we have is, if I want to write this, I can do this thing minus 1 plus t omega naught okay, and this entire thing, let me just write it like this, minus omega naught squared xp over t plus omega naught squared xp is equals to f naught over m cos omega naught t. Okay, so now if we compare the left hand side and right hand side, we see that here we have a cos term and here we have both sine and cos. Okay, so this requires that our a goes to 0, and our 2b omega naught. So on left hand side we get 2b omega naught. Okay, and this should be equals to f naught over n. Okay, so finally we get, so the solution xp of t, which is f naught over 2m omega naught t sine omega naught t, is the desired solution for the, so this is for case of omega equals to omega naught. Okay, so for and this is the condition for resonance. Okay, okay, so now if we look at the options, we can see it matches with option C, right? And one thing to note that this xpt, so the amplitude here, okay, so the amplitude that we are getting, if I just write the amplitude, that is coming out to be f naught t over 2m omega naught, and you can see that it is directly proportional to t. So what this means is, as our time progresses, our amplitude keeps on diverging. Okay, and this is the condition of resonance. Okay, so it is not a constant, it is not damping, but it is always increasing with time. Okay, so now let's solve the next problem, and this problem is for a damped forced oscillator, but I think the damped force oscillator was not exactly discussed in this class, but this is a pretty simple problem, so we can solve it anyway. So here you can see we have an additional damping term 2 gamma, and at exact resonance its steady state amplitude is already given to us. So the steady state amplitude A omega naught is given to us to be equals to F naught over M to gamma omega naught. And F naught over M is given to be as 10, gamma is given to be 0.5, and omega naught is given to be 5 radians per second. So these two just cancel out, and the amplitude is just 2 meters. Okay, so we get 2 meters as the amplitude. Okay, so here if you notice, this is also a case of resonance, but the point is when we didn't have any damping term, the amplitude was ever increasing with time. But as soon as you add a damping term to the case of resonant oscillator, there is no time dependence in the steady state, right? And the amplitude just becomes constant after some time. And this will be discussed in the week 6. So we'll solve a few more problems based on the damped forced oscillators next week. So I just wanted to give you some idea that this amplitude, it diverges when there is no damping, but as soon as you add a damping term, you can see that this amplitude again becomes a constant for the steady state. Okay. Now we have looked at forced oscillators. We have also looked at one problem where we had both an external force and damping. But now we'll solve a couple of problems where there is no external force, but there is a damping that is involved. Okay, so we do not have a forced oscillator, but we have a damped oscillator. Okay, so we are given the equation that a damped oscillator obeys. So x double dot plus 2 gamma x dot plus omega naught squared x is equals to 0. Okay, this is the equation given to us. Okay, and let us try to find out the solution of this equation. So straight away you can see that if I try an exponential function, what will happen is I'll get the differential. So the first differential will again give me an exponential function, and second differential will of course give me another exponential function. So that looks like a possible solution. So to begin with, let us try an exponential function e to the power lambda t. Let's try this out. So the second derivative will give me lambda squared e to the lambda t plus 2 gamma lambda e to the lambda t and omega naught squared e to the lambda t is equals to 0. So I can cancel out this e to the power lambda t, and the equation that I get is lambda squared plus 2 gamma lambda plus omega naught squared is equals to 0. And this is a quadratic equation, right? And the solution of this quadratic equations, I'll get two solutions, which will be minus gamma plus minus under root gamma squared minus omega naught squared. So I get these two values of lambda. Okay, and you can notice that if I put this back into my equation here, I can write my x as e to the power. So I'll have this lambda, which will be minus gamma plus minus under root gamma squared minus omega naught squared, and then I'll have a time here t. Okay, so now the question is asking that if the motion is oscillatory under damped, what condition needs to be satisfied, and we are given a bunch of conditions. Okay, so let's look at all these conditions one by one. This is what we have as of now. So for the first case, we can have our gamma being less than omega naught. Now what will that do? So we have this term here, right? This, let's focus on this term. If gamma is less than omega naught, this term will be negative. And when we take the square root of that negative number, we'll get some imaginary quantity, right? So because this term is negative, this will imply our lambda will be minus gamma plus minus some iota, some frequency omega d, right? Where omega d is real, right? And because of this iota coming outside, right? So what we can do, we can write our solution x as e to the minus gamma t, and then e to the, let's say, some iota omega d t. Okay, of course plus minus sign is there. So this term decays exponentially, but this term oscillates, right? What this means is our amplitude is constantly decaying, but still we have some oscillations. So our oscillations will look something like this, and they are decaying with time. Okay, something like this, and they are decaying exponentially. Okay, so that is what this means. Okay, so this is when omega is less than omega naught. This is the case of under damping. Okay, now let's consider the second case, when then where this gamma is greater than omega naught. So then what will happen, this term, this time this term will be positive, and we will not have any imaginary iota coming outside, right? So all we'll have is this, all we'll have is the function with form e to the power minus some gamma effective t, right? And there is no oscillation. Okay, and there is only a decay. So this is called overdamping, right? So this is called overdamping. And our, there is no oscillations, and our function just decays. Okay, our function just decays exponentially. That's it. We do not have any oscillations. We can also have these two as equal, where gamma is equals to omega naught, and then if you put them as equal, you can see that our x is simply e to the power minus gamma t, and again there is no oscillatory behavior here, and this condition is known as critical damping. Okay, and this is called critical damping because this is the fastest way of damping, as gamma effective is always less than gamma. Okay, so the system damps most quickly when this condition is matched. Okay, so these are the three possible conditions, and for oscillations we now know that gamma has to be less than omega naught. So if I look at the options, the motion is oscillatory under damped provided, and gamma is less than omega naught, so option D. Okay, and because they have mentioned under damped, so the correct option is option D. Of course, if gamma is 0, then also the motion will be oscillatory, but it will not be under damped. Okay. So moving on, we have a damped oscillator, and the equation, the solution is given to us. So we are given that x of t is e to the minus 2t, 3 cos 4t minus 2 sin 4t. And we have to find out its equation of motion. Okay. So the general solution of a damped oscillator, let me write for a damped oscillator, the general solution is given as x of t is e to the minus gamma t. This is the damping which we were talking about. And then we have the oscillatory part, a cos omega dt plus b sine omega dt. Okay. And this omega d, which we just found out here, this is the frequency, right? Omega d is nothing but omega naught squared minus gamma squared. That is what we have. Okay. And corresponding to this, the equation of motion is given as x double dot plus 2 gamma x dot plus omega naught squared is equals to 0. So now if we compare this equation and this equation, clearly we can see on comparing clearly gamma is 2, right? And omega d is 4. Okay. So my omega naught squared will be 2 squared plus 4 squared, and this is 20, right? So my omega naught squared comes out to be 20. So I have this value, and I'll just substitute back in the equation of motion. So I get x double dot plus, now this 2 gamma will give me 4x dot, and omega naught squared is 20, so plus 20x is equals to 0. So I get this equation of motion. Let me check the answers, and it matches with option A. Yeah, okay. So for the next problem, we are already given that this gamma is 0.1 per second. We are given that the damped period Td is 2 pi, and we have to find the ratio of the amplitude one damped period later to the initial amplitude, ATD over A0. Okay, so we know that the general solution for the damping, we can write it as C e to the power minus lambda t cos omega dt. Let me write it again. We have this, and this is the amplitude, right? So this is the amplitude, and it constantly decays with time, right? It is decaying with time exponentially, so it exponentially decays with time. So the amplitude at successive damped periods shrinks by a factor each time. Okay, so if I compare at t is equals to 0 and t is equals to td, so my a at td is simply c e to the power minus gamma td, and my a at t is equals to 0 is simply c. So if I take this ratio, dividing both of them, what I get is this exponential e to the power minus gamma td, right? And this gamma is 0.1, td is 2 pi. So just plugging in these values, e to the power minus 0.1 into 2 pi. So let me calculate. Okay, so this is e to the minus 0.628, and if we calculate this value, right, so we get this ratio as 0.53, which means that it has decreased by roughly half. Okay, 0.5. So for a damped oscillator with gamma 0.1 and td is 2 pi, this results in a damping of our amplitude by almost half with what we started. Okay, so yeah, that was it for the damped oscillator, and now we'll solve a couple of problems related to phase space and motion under a harmonic potential. Okay, so now coming back to simple harmonic oscillator, we are given a simple harmonic oscillator, mass is 2 grams, omega is 5, total mechanical energy this thing. So we have to find the area enclosed by its trajectory in phase space, okay, the xv plane. We have to find out the area. So for x of t being equal to a cos omega t minus phi, let's find out the velocity. The velocity is given as v of t, which is nothing but derivative of x of t, and we get minus a omega and sine omega t minus phi. So we get this velocity. Okay, so what we can do, we want to use the identity using cos squared some theta plus sine squared theta, that is 1, right? We use this identity. So here we have this cos term and here we have this sine term. So this would imply, so cos squared of this theta is nothing but x squared over a squared, and here we have this, for sine term we have vt and a omega, so plus v squared over a squared omega squared, and this is 1. Okay, so this is what we have. And just looking at this equation, okay, you can see this is nothing but equation of an ellipse. Okay, this is the equation of an ellipse in the phase space. And phase space is nothing but our xv plane. Okay, so if I have this as my x-axis, and this as my velocity axis, and if I now draw an ellipse, okay, so this is an ellipse. So at v is equals to 0, my x squared is a squared, right? So x is plus minus a. So this distance is a, right? This semi-major axis. This distance is a. And at x equals to 0, my velocity is simply a omega. So this distance is then omega times a. Okay. So this is what I have in my phase space. This is how my simple harmonic oscillator looks like. Okay, so now generally for an ellipse, okay, for an ellipse, the general equation is x squared by a squared plus y squared by b squared is equals to 1, and the area of this ellipse is simply pi times a times b. Okay, so now if we compare to our case, so that is the equation. So for our case, the area will be pi times, now this semi-major axis is a and semi-minor axis is a omega. So the area of this ellipse is nothing but pi a squared omega. Okay, so this is what we have. Okay, but in the problem we are given omega, we are not given the amplitude. What we are given is the mass and energy of the particle. So we can write this area instead of using amplitude, we can use energy and mass. So let us change that thing. We know that energy of a simple harmonic oscillator, E, is nothing but half m omega squared a squared, right? So this implies a squared is nothing but 2e upon m omega squared. And now we can substitute this back, and finally we can write our area as pi omega multiplied by 2e over m omega squared. So this omega cancels out one of the omega, and finally our area becomes 2 pi e over m omega. So this is the area our simple harmonic oscillator spans in the phase space. Now E is given as uh, E is given as 50, right? E is 50 ERG, mass is 2 grams. and omega is 5 radians per second. Okay, so plugging in all the values, our area becomes 2 pi times 50, mass is 2, and omega is 5. Okay, so this becomes 10, and this 10 cancels out here, so this becomes 10 pi. So area is simply 10 pi, and we know pi is 3.14, so this is roughly 31.4 centimeter squared per second. No, just centimeter square per second. Okay, notice that we are writing area, but the units are centimeter square per second because we are in the phase space. So this x-axis has dimensions of centimeter and y-axis has dimensions of centimeters per second. So x times v will give us centimeter squared per second, right? So 31.4 centimeter squared per second, which matches closely to option B. Okay. Okay, so question 15, which is the last problem for today. So here we have a particle of mass 1 kg, and this moves under an isotropic harmonic central force. So we are given that there is a central force F of r, which is nothing but minus 4r. Okay, and we are given angular momentum L is 2 kg meter squared per second. Also, we are given that the total energy E is 6 joules, and we have to find out the turning points of the radial motion. Okay, so clearly when we look at the form of this force, we see that it is proportional to minus r, which means that it is a simple harmonic oscillator. Okay, so this is the isotropic harmonic central force, and its potential, if you want to write the potential, so our potential V of r is simply half k r squared, right? So for f of r is equals to minus k of r, we get this potential. Okay, and now because this is a radial force, so this is a radial force, so we can write out our effective potential V effective of r, that will be nothing but half of k r squared, which is our potential, and the angular momentum centrifugal term, right? L squared over 2 mr squared. Okay. So we can see there is a competition happening between the first term and the second term. Okay. So what is happening as r is increasing, this term is decreasing and this term is increasing. And if r is decreasing, our first term increases and the second term decreases. Okay. Okay. So the question asks us to find the turning points of the radial motion. Okay. So the question asks us to find the turning point of the radial motion. So at turning points, our velocity becomes 0, right? So r dot is 0, and this implies that all the energy of the particle is only stored in this effective potential, right? There is no kinetic energy of the particle at turning points, right? So our energy E then becomes k r squared over 2 plus L squared over 2 m r squared. Okay. Now we want to solve for r, right? We want to find out at what value of r do we actually have a turning point. So this is the equation that satisfies those value of r. And let us find out what value of r we can get. So first of all, let us substitute x equals to r squared. So let x is equals to r squared. That will give us energy E as kx over 2 plus L squared over 2mx. Now we can multiply by x on both sides. So we will get Ex is equals to kx squared by 2 plus L squared over 2m. So we get a quadratic equation. Now let's also multiply by m. So m will go here and here. And if we also multiply by 2, so this 2 vanishes and we get this equation. Okay, so we get this equation. So if I now rearrange this equation, I can write mkx squared minus 2m ex plus L squared is equals to 0. Okay, and this is the quadratic equation, and I can easily solve the using the quadratic formula. Okay, so I get these two solutions of x, and now we are ready to plug in the values. So we are given m as 1, L as 2, E as 6, and K as 4. So if we now start plugging in the values, so this becomes 6 over 4, right? This becomes 6 over 4 plus minus under root. This becomes 6 squared over 4 squared minus, so L squared, L is 2, so this becomes minus 4, and M is 1, so 1, and K is 4, so 4. So this is just 1. Okay. So then my x becomes, so this is 3 by 2, so which becomes 1.5 plus minus under root. So this is 1.5 squared, which is 2.25, right? 2.25 minus 1, which is roughly 1.5 plus minus 1. This is roughly 1.118. Okay, so I get two values of x. So if I add, I get 2.618, or I get 0.382. Now because r is under root x, so I get r as under root 2.618 or under root 0.382. So if we calculate these roots, what you will find out is that R is roughly 1.618 or 0.618. So we get these two values of R. So roughly 1.6 and 0.6. So let's see if it matches with some answers. Yes, it matches with option C. So these are the turning points of our mm, particle. Okay, right. Hmm. Okay, so yeah, this was the last problem for today. And with that, we'll end today's session. And with more problems, I'll meet you guys next week. Okay. Yeah, you're welcome. So I'll see you next week. Bye bye.